Today I'm going to talk about buoyancy and Archimedes' principle in section 8.4. So the first thing I want to look at is three observations that tell us that when an object is submerged in a fluid, there must be an upward buoyant force acting on it. Okay, so let's consider that we drop an object that is less dense than the fluid into the fluid. Initially, that object will raise upwards, it will begin to float, and then it will come to a rest, maybe partially submerged in the liquid. This tells us that there's some upward force that's supporting it and causing it to float upwards. And that must be the buoyant force, or that is called the buoyant force. Second example is if we were to drop an object that is more dense than the fluid into a fluid. It will sink in the fluid, so it's going to drop downwards, but it will drop at a rate less than the acceleration due to gravity. So that means there must be an additional upward force acting on it, which again is evidence of the buoyant force. Okay, the third example is if we were to allow that object to come down to the bottom of the container and somehow we could measure the normal force there. What we would find is that the normal force is less than the object's weight. So this again means that there's another upward force acting on the object, and that force is called the buoyant force. So let's come up with some math for this upward force in the fluid. To do this, let's consider a cylinder of some substance that's immersed in a fluid. So here's the cylinder. It has cross-sectional area A and height H. Since it's submerged in the fluid, we know that the pressure at the top of the cylinder is P naught, and at the bottom is P, and we know P naught will be less than P since pressure increases with depth. So if we just look at the net force due to the fluid, I'm going to ignore gravity right now to come up with an expression for the buoyant force only. We have the force on the top, F down, will be due to this pressure at the top of the region, P naught. So we have P naught A, since F equals pressure times area. And at the bottom, pushing up, we have the force is pressure times area, but it's P, the pressure at the bottom of that cylinder. Okay, so our net force due to this pressure gradient will be the buoyant force equals F up minus F down, PA minus P naught A, and then we can factor out the area here. So P minus P naught A. Now for this absolute pressure at the bottom, I can plug in the hydrostatic equation here. So we're looking at fluids again of constant density. So the hydrostatic equation here is for the absolute pressure P, and then P naught will cancel, and we're left with rho F G H A. The height times the area of this shape is the volume, so we can plug that in. The buoyant force is rho F Vg, and this gives us two expressions that are very important for the buoyant force. When an object is submerged or partially submerged in a fluid, it will displace an amount of that fluid that's equal to the volume submerged. If it's completely submerged, it will displace an amount of fluid equal to its own volume. If only part of it is submerged, it will displace a fluid equal to the volume of the object that is submerged. So what we see here is that we have rho F, the density of the fluid, the volume, this is the volume of fluid displaced, times G. And that gives us the buoyant force in newtons. So we could also write it as this, the buoyant force equals the mass of the fluid displaced times G. And that's just replacing density times volume by the mass of the fluid that's displaced when that object is submerged or partially submerged in the fluid. And now we have an expression for this upward force that acts on the object in the fluid, and it's called the buoyant force. So there may be other forces acting on the object as well, and as we go into solving problems, we'll look at writing the net force considering all of those objects involved, including gravity. So this is just the buoyant force, and this also is Archimedes' principle. So Archimedes' principle says that when an object is submerged or partially submerged in a fluid, the fluid exerts an upward buoyant force, Fb, on that object, and the magnitude of the buoyant force is equal to the weight of the fluid displaced. So our relationship here displays Archimedes' principle clearly. Okay, let's look at some examples. All right, the first example, an object is held beneath the surface of a fluid. The object has a mean density ρO and the fluid has a density ρF. Demonstrate the relationship between ρF and ρO if the object floats, so rises, sinks, or stays put, stays at rest. All right, so let's draw a free body diagram to analyze each case here. We know, based on observation, what the relationship between the densities should be, but let's see if we can prove that using Archimedes' principle. Okay, so in the first case, if we put this object fully submerged in the fluid and it rises, it floats, that means that there must be an upward net force acting on the object. So we have the buoyant force up and Fg down, and the buoyant force must be greater than the weight. Now, let's look at the expressions. The buoyant force we showed is ρF Vg. The weight is the mass times g. Many times in this section we'll replace mass by density times volume. So we can do that here for the object as well. We have the density of the object times the volume. Also notice that since this object is fully submerged, the density of the fluid displaced is the same as the density of the volume, so we don't need a subscript there. All right, so the net force in this y direction has to be greater than 0, which means that the buoyant force minus Fg is greater than 0, or the buoyant force is greater than Fg. Then I can plug in each relationship for Fg and for the buoyant force. So ρF Vg is greater than ρO Vg, and this volume times g cancels, and we're left with this relationship for the densities. So as we'd expect, if the object floats in a fluid, it means that the fluid is more dense than the object. So the object then is less dense than the fluid. Okay, so part B asks us, what if it sinks? I can just adjust my mass slightly here to show what happens if instead it sinks. If it sinks, we know that there's a net force downwards, so gravity is going to be less than the buoyant force. So I'll just reduce my arrows to demonstrate that. And that means that our net force is downwards here since our object was dropped and it's starting from rest in the fluid. Okay, so this is less than 0. And I can switch all my signs here because all of this would hold true. Our net force has to be less than 0, so it accelerates downward. And then we have FB less than FG, and we have plugging in the expression for each force, we end up with less than signs all the way down. So similarly, this means that if the object sinks, the density of the fluid is less than the object, or the object is more dense than the fluid. All right, one more case. What happens if the forces are balanced? So this object is submerged, and then it remains at rest. Okay, so we've got these forces balanced, and I'm just showing you the relative size of them. There's no meaning to the length in terms of the weight. But okay, so those forces are balanced. That means that if it's going to stay at rest, the net force is equal to 0. So because of that, we must have the buoyant force equal to the force of gravity. So all of these signs have to change to equals. And so as we'd expect, if the object remains at rest in the fluid, completely submerged, that means that its density is equal to the density of the object. Anytime we have an object that is at rest in a fluid, that can be called neutral buoyancy. It doesn't have to be this case. If the object is less dense than the fluid, it could come to a rest partially submerged in the fluid. So not completely submerged, part of it would be above the surface, and that could still be called neutral buoyancy. All right, let's try another example. A block of wood of density 540 kilograms per meter cubed is dropped into water. The wood has a cross-sectional area of 100 centimeters squared and a thickness of 15 centimeters. How far will the block submerge into water? How much mass would you have to add on top of the wood so that the surface is just at the water level? All right, so I've drawn this here. We know the density of the wood is less than the water. I'm going to call it rho O and rho W for the water. O for object, meaning the wood. So it's less. So once it's dropped in, it will float, and then it will eventually come to a rest at a point where part of it is out of the water. So it's only partially submerged like this. We want to find D, the height that is of the object that is submerged under the water. Okay, so for all buoyancy problems where something comes to a rest, this is really just a Newton's first law problem. So we want to set the net force in the y direction equal to 0. And we can start like that for almost all of our buoyancy problems. In this case, there's only two forces acting on this, an upward buoyant force and its weight. So we have FB minus FG equals 0, or FB equals FG. So I can plug in on either side. Rho F Vg for the buoyant force equals density of the object V naught times G. And this is the mass of the object, which if I had, I could put it there, but instead we have the density and dimensions to find the volume. So we might as well plug that in. Also notice that I've labeled subscripts. So when the object is only partially submerged, those volumes aren't equal. The volume of the fluid displaced is equal to the volume submerged. It's equal to this volume of the object, but not the entire volume of the object. That's only if it's completely submerged. Okay, so let's plug in volume equals area times the height. So for the part submerged, that's area times D. The total object, it's area times H. Notice now this area is constant. It will cancel, and so will G. So I'm left with just rho D equals rho O times H, and we can solve for D. So we end up with the ratio of the densities times H, so 540 over 1,000, they're both kilograms per meter cubed, times the height of 15 centimeters, and we get 8.1 centimeters. So it will submerge until 8.1 centimeters are below the surface of the water in regards to its height. This is kind of a general result. So if those were the only two forces acting on the object, it will come to a rest with an amount of the object under the water that's equal to the ratio of the densities. That could give us the fraction of the height under the water. All right, so the next part we're asked if we were to add a mass on the top of the wood, how much mass would we have to add so that it is just at water level? So I'm just going to change this diagram up here. Now it looks like this. The wood is at the water level, so this is H, and we've placed an extra mass on top. So now on that block of wood, there's an extra force. It's this added weight. So we'll have Fg of the wood plus Fg added, and then just the buoyant force acting upwards. So we do need to add one more force in our net force in the y direction. So the net force equals 0. I have Fb minus Fg of the object, the wood, minus Fg added equals 0. Then I can plug in the expressions here. The buoyant force is the density of the fluid, the volume, times G, minus our weight of the wood, density of O, times the volume, times G, minus the mass added we have. So we're trying to find it. So we can plug mass added here, times G, equals 0, since we don't know the density of the mass we're going to put on top. All right, and then this is our unknown. G is in every expression, so we can cancel G. And this time I haven't distinguished between the volumes because now the wood is completely submerged. So the water will displace a volume equal to the volume of the wood. And we can plug in that volume. It will be area times height. So I'll get the mass added equals, I'm moving this over so everything keeps the same sign, rho F V minus rho O V, which will be rho F minus rho O, area times height. And at that point, we can just plug in the numbers in order to solve. So our densities are 1,000 minus 540. That's kilograms per meter cubed. And then we'll have times the area. It was 100 centimeters squared, so that's 0.01 meters squared. And then times the height, 0.15 meters. Okay, and I'll put the answer here. That gives me a mass of 0.69 kilograms. So again, we started with Newton's first law and then wrote out the net force acting on the object and set it equal to 0, making sure to account for the buoyant force and any other forces that were acting on the object. All right, let's do another example. What radius must a helium balloon attached to a 200 kilogram basket have to float with neutral buoyancy in the air? Assume that the balloon itself has a negligible mass and that the basket displaces a sufficiently small volume that its buoyancy is negligible. And then we have the density of air and the density of helium. Okay, so for this balloon, there are only 3 significant forces. We have the buoyant force of the helium within the balloon. We're asked to ignore the buoyant force of the balloon, which would be very, very tiny since it would be light and thin. And then we have the weight of the basket and the weight of that helium in the air. Now this balloon is fully submerged in the air, so it will displace a volume equal to its own volume. And we have the net force is 0 since it's floating with neutral buoyancy. It's at rest or moving at a constant velocity. That could mean that as well. Okay, so we have the buoyant force minus Fg of helium, its weight, minus the weight of the basket equals 0. So rho air Vg minus rho helium Vg minus the weight of the basket equals 0. So then we have the balloon, volume of the balloon equals, notice I cancel G, it's in every term. So the volume of the balloon is the mass of the basket divided by rho air minus rho helium. And you can try rearranging that yourself. Now, we want to find the radius of the balloon, so we can plug in the expression for the volume of a sphere, which is 4/3 pi r cubed. So I'll just rearrange and plug in the numbers. I'm going to erase this on the top, but you can pause if you need to. All right, so here I get r cubed equals 3 m basket over rho air minus rho helium times 4. There we go. 4 pi. Okay, so we can, here, I'll write that more clearly. 4 pi. So then I'm going to take the cube root. So I'll have the radius is the cubed root, 3 times the mass of the basket over rho air minus rho helium, and I'll put the 4 pi here. Okay, so that's the cubed root of 3 times 3.2 kilograms over 1.28 minus 0.17 kilograms per meter cubed times 4 pi, which gives a radius for the balloon of 3.5 meters. All right, next example. When a crown of mass 14.7 kilograms is submerged in water, an accurate scale reads only 13.4 kilograms. Is the crown made of gold? The density of gold in air is 19,300 kilograms per meter cubed, so we can determine the density of this crown by using the buoyant force and the net force acting on it, and then compare to that density of gold to determine if it is in fact gold. All right, so the weight of this crown, its true weight, is Fg, which equals mg. However, when it's submerged in a fluid, it will experience a different weight called an apparent weight. And in this case, you can think of it as a spring scale, so something that you would suspend an object from, and then it would measure the tension, and that tension would give the apparent weight. You can see if there was no buoyant force that our spring scale would give the weight because the tension would be equal to the actual weight. Okay, so our net force is the tension or the scale force, however you want to think about that, and then the buoyant force upwards as well, and the weight downwards. So again, it's at rest, we can set our net force equal to 0 in the y direction. So we have the tension and the buoyant force up minus Fg, which is down, equals 0. Okay, so our tension is this force here. It's our scale reading, which is the apparent mass times g. So I've labeled it mw to mean the mass in water times g. Then I have the buoyant force, the density of the fluid, water, times the volume of the crown, or the volume of the object submerged, g, minus the true mass, m, times g. Now what we want to do is solve for that volume of the crown so that we can use its true mass to then determine its density. Okay, so g will cancel everywhere again, and then I can solve for the volume. It's mw minus, or the true mass minus mw over the density of the fluid. Subtracting them divided by 1,000 kilograms per meter cubed gives me 1.3 times 10 to the negative 3 meters cubed. So to calculate the density of the crown, we take the density, the true mass divided by the volume to get the density of the object, 14.7 kilograms divided by 1.3 times 10 to the negative 3 meters cubed to give me 11,300 kilograms per meter cubed. And that's definitely not gold, but if you look at a table of densities, you'll find that this is potentially lead. That looks close to lead. This is similar to the one example I said that shows us that there is a buoyant force, right? Our weight is reduced, or the apparent weight is reduced when the object is submerged in the fluid. Okay, one more example. What is the likely identity of a metal if a sample has a mass of 63.5 grams when measured in air and an apparent mass of 55.4 grams when submerged in water? Okay, so this looks really similar to the previous example. We need some kind of scale force to measure the mass of the object, and since it's submerged in a liquid, I think it makes sense to think about a spring scale again. So our apparent weight force will be this tension. The buoyant force is upwards, and then the weight is downwards on the object. So writing out the net force equals 0, looks like the last question, Ft plus the buoyant force minus Fg equals 0. The tension is this apparent mass, so the mass in water times g, plus the density of water, Bg, and again it's fully submerged, so that's the density of the object, minus the mass times g, the true mass, to give us the weight equals 0. Okay, so g will cancel, and solving for the volume again, we have the difference in the masses over the density of the fluid. We're given the masses in grams, so I might as well use grams per centimeter cubed here for the density. You could convert to kilograms. It's very similar. So the density of water is 1 gram per centimeter cubed. So dividing that, we get 8.1 centimeters cubed for the density of that object. Okay, so to calculate the density of the object, we take the true mass, 63.5 grams, over that volume, 8.1 centimeters cubed, which gives me 7.84 grams per centimeter cubed, or 7,840 kilograms per meter cubed. And again, if you look up a table of densities, what you'll find is that this is probably iron or steel. Okay, so I just wanted to make one more note that when we do measure the true mass of a substance, technically that should be in a vacuum. We take scale measurements usually in air. We're always in air in real life. And we can ignore in general the buoyant force of air unless we're talking about the force on gases, something of a smaller density as well. In this case, if you calculate the buoyant force from air acting on the object, you'll get a force on the order of 10 to the negative 7 newtons. So you can see how that is so tiny that we can take the true mass in this case to be the mass in air. Okay, that's all for now. Let me know if you have any questions.